All right? So with this idea of radians, we're now going to talk about angular motion. All right? So first we're going to talk about angular displacement. So angular displacement is the angle through which an object passes during its circular motion. So if I have, going back to the beginning, let's say that I have my person here, and they're playing with their rock on the string, and the rock swings around this far, the angle that it has gone through, that is your angular displacement right there. Okay? So we have our angular displacement. That's just the angle that it's gone through. It's not a length, it's the angular displacement. How far has the angle gone through? Now, you can recognize that as you go around, you could go all the way around the circle from the beginning, and when you got back to the beginning, you would have traveled a distance of 2 pi radians. However, you would be back to where you started from. Okay, so your overall displacement is 0, though you have rotated through 2 pi radians. And we'll use both of those ideas later on. Next, we want to talk about angular speed. Well, you know that speed is just distance or displacement over time. And so we're going to define the angular speed. Angular displacement is just theta. How many radians have you gone through? It's very rare that we talk about degrees here. Okay, that's why it was very important that we talk about radians in that prior page. So we'll talk about an angular displacement in terms of radians over, and then when we calculate the angular speed, it's just your angular displacement over time. Or in other words, average angular speed, which is omega here, this is a lowercase omega, equals our angular displacement, which is theta, that's the angle that it's rotated through, over time. All right? Now, that will give us how many, if you look at the units, if we put our angular displacement in radians and our time in seconds, that means that it will be telling us how many radians per second we're going through. All right? Now, this, of course, leads to a couple other things which we'll look at shortly. But first, I want to talk about a couple other small topics, namely angular velocity. You notice that we defined this as being the angular speed. And that's very, very important that we're defining as a speed, not a velocity. You actually don't have to worry about angular velocity in the core of this course. You do talk about angular velocity when we get to the option, the engineering option. And you may look at that later if you choose that option for your IB. But otherwise, you don't have to worry about angular velocity. The thing with angular velocity is that angular velocity is the result of a cross product. And those who are in math may have found out that a cross product results in a direction that's perpendicular to what you're doing. And we'll talk about that more later, but it's perpendicular to the direction of your motion and the force, and so it actually ends up being completely out of the plane of motion, which makes things a little bit interesting. We'll talk about that more if we get there later. All right, so let's just double check really quick and make sure that we're understanding our ideas here. So we've got Big Ben, though technically this is not right. Big Ben is actually the bell inside Big Ben clock. So we'll talk about the clock on Big Ben and a little alarm clock. You can see the little alarm clock down here, right? There he is. Isn't he so cute? Oh, my pencil's not working. Oh, there he is. There's my little alarm clock. Both keep perfect time. Okay, exactly in correspondence with each other. Which minute hand has the bigger angular velocity? Go ahead and pause the video and think about it. When you unpause, I'll give you the answer. All right, so you should have chosen an answer. Please make sure that you're actually taking time to do this. It's very important for your learning and for your understanding that you take time to try to answer the question and commit to it before you move on. So now that you've chosen an answer, we'll give you the answer. A lot of people think that Big Ben is going to have a higher angular velocity or angular speed. This should say speed. That's not true. The angular speed depends on how fast of the angle you're going through, right? Angular speed is theta over time. Sorry, not r. Theta over time. And you'll notice that in the same amount of time, both clocks will go through the same rotation, their minute hand, right? They'll go from the time to quarter past in exactly the same amount of time, and the angle that they pass through will be exactly the same. From 12 down to the 3, they'll both go through a 90-degree angle, which means that they're going through, or not 90 degrees, we're using radians, so that'll be pi over 2. And so the angular velocity for both of them, the angular speed, will be the same. Now, we're not talking about directions, so don't worry about the fact that it says velocity instead of speed too much, but they will be exactly the same. All right, let's try another one. Read the question, pause the video, and then unpause to get the answer. All right, so here the key is recognizing that as this rotates, it's going to cause the belt to move, right? So when this rotates, it's going to go that distance right there, okay? So it's going to go all the way around, which means within that amount of time, it's going to go 2 pi radians, right? All the way around the circle in that amount of time, that specific amount of time. Now, that means that the belt itself will travel that far. Now you can tell on the bigger circle that that distance is not going to be very far, right? We don't know the exact ratio, so we can't really say how much farther it will travel or how much less of an angle it'll go through. But if I take this length right here, one time around, and stretch that length of belt over here, because the belt can't go faster on one wheel than it goes on the other. The belt has to travel the same distance, the same speed. So you can see that the angle here is much less than the one over there. If I were to estimate, this is about pi, so maybe if I estimate about 2 over 3 pi or something, that would probably be my best guess as to the angular displacement. Same amount of time. Of course, that means that WL is going through is much smaller, right? Your angular speed or angular velocity is going to be much, much less. And so, therefore, our answer should be B, that the angular speed of WS is much greater than that of the omega L. Okay, I know I said W, it doesn't really matter. Same thing. All right, let's go on. Okay, so let's look at a couple other terms that are associated with that. The first is period. Now, you should be somewhat familiar with period already. Period is the amount of time that it takes your object to go around the circle one time, right? So period is just an amount of time, all right? Now, of course, if we're thinking about that, we can then relate it to this, right? So period is time to do one rotation. 2 pi is the angular displacement, the amount of time, the amount of angle it has to go through for, again, we're talking about one rotation for the period. So the angular speed, remember speed is just theta over time, or in other words, the period is 2 pi over your angular speed, or angular velocity. Okay? So in this case, we'll go ahead and recognize that the period is equal to 2 pi over omega. All right? The other thing that we want to talk about right now is the frequency. Okay? So the frequency is how many rotations it goes through in 1 second. And so if that sounds kind of familiar, it should, because the period was time for one rotation, right? And then the frequency is how many rotations in 1 second. So you may be able to recognize that frequency is just the opposite, the inverse, the reciprocal of the period. Okay? So when we define frequency, frequency will be 1 over the period, or the period will be 1 over the frequency, either way. Now the units of frequency are called hertz. And we'll use this a lot more when we do waves and electronics and things like that, but it applies to circles as well, because hertz, the units of hertz, is cycles per second. Okay? So that's your SI unit for frequency. Okay? Not fundamental, obviously, it's not fundamental. It's a derived unit, but we can use that for cycles per second. All right? Now the last thing we want to do is we want to be able to link our angular and rotation and the linear speed, okay? Because a lot of time we'll have the speed. So let's see if we can kind of figure that out. All right, so let's look at that. We know, ooh, that's not really what I wanted to happen. There we go. We'll just move that out of the way. We know that the linear velocity, v, equals distance over time, right? We also know that the angular speed or angular velocity, if we're not worried about the direction of our angular velocity, is equal to the change in angle over the change in time, right? Okay, well, if we're thinking about our angular displacement, if I can write that in terms of a distance, that will be very helpful here. Okay, now if we think about it, if I have a circle and I have some type of angular displacement, how far has it traveled? What is the distance? Now, we said that the angle will correspond directly to the number of radians if we're in radians. This is one of the reasons why it's so important that we use radians, not degrees. Okay? If I rotate through 1 radian, then my distance is the distance of 1 radius. Okay? Now, if I go through 2 radians, then the distance traveled will be 2 radii. Okay? And so I find out that the angular displacement is corresponded directly to the total distance traveled. Okay? So the distance traveled is going to be equal to the angular displacement, okay, which is in radians, times the length of the radius, right? Because if I go 1 radian, I go through 1 radius. How far is that? Well, it's the length of 1 radius. Now, if I take this and I put it into the distance, then what I have is that v equals theta r over t. And you'll notice that I there have theta t, which means that v equals theta t being omega, v equals omega times r. Now, this only works, remember, we did this assuming that our angle was in radians, and that the total distance then was the length of a radius times how many radians we went through. That is the beauty of radians, and that, my friends, is why we use radians and not degrees, because degrees, I have no idea what the actual value of it is, other than the fact of the rotation of the Earth, which then isn't even exact, as we talked about. So, please use radians whenever you're in physics, unless it gives you degrees, in which case you can work with degrees. But use radians because that makes these formulas work. And we just found out that the velocity is equal to the angular velocity, or the angular speed, times the length of the radius. All right, let's go ahead and move on.